Okay, so in this lecture, we are going to study two very important topics related to group theory. One is lattice diagram, the lattice diagram. So this will be the first topic we will be studying, and the second topic we will be studying is the concept of conjugacy in the symmetric group essay. So these two topics are which we are going to study today. So let us start with the first one. Okay. So the concept of a lattice diagram. Okay. So before moving on to the concept of a lattice diagram, we first emphasize on two very important topics related to the order of an element in a finite group. So let me just state this as a lemma. Okay. So suppose let G be a finite group. Let G be a finite group and let A be an element in G such that the order of A is, let's say, n. Clear? Then if the GCD between, or let me just directly write out what the lemma says, then the order of any power of A, say a to the power k, it's given as n divided by the GCD between n and the exponent k, where nk represents the GCD of n and k. So this is basically order of A divided by the GCD of order of A and K. Okay. So this is what we actually want to prove. And obviously notice that if we have established this lemma, then we have an immediate corollary of it. And the corollary says that order of A is equal to order of A to the power K if and only if the GCD between order of A and the exponent K is equal to 1. Clear? So if you have established this fact, then this fact is pretty easy to observe. As you can obviously notice that, so if order of A is equal to n and n k is equal to 1, then obviously you can have integers say s and t such that ns plus kt is equals to 1. So you can establish this part from here. Clear? And this implication is trivial from this case, right? Rather, I said a bit wrong. This implication you can try out in this form. Yeah. This implication you can try out in this form. And this reverse implication is this is pretty trivial from this level, right? So obviously we will be proving the first lemma only. So let's start with the proof. Okay, so proof. Clear? So the first thing we do is obviously we are given that the order of A is n, right? Let nk have the GCD. Clear? So what we actually need to prove? So we need to prove that the order of A to the power k is n by d. Right? This is what we need to prove. Clear? Okay. So observe that since the GCD of n and k is d, then that implies there exists or rather I should say, then that implies D divides N and D divides K from the definition of a GCD. So therefore, there exists integers alpha and beta such that you can write N as D beta and K as D alpha. Right? This is what you can do. Clear? With beta and alpha having the GCD1. Right? They are co-prime. Got it? So this result is pretty trivial from the definition of a GCD, right? Now, so we have K written as D alpha, right? Now, obviously observe that A to the power K to the power N by D, right? So this is equals to A to the power N times K by D, and K by D is nothing but alpha, right? So this is nothing but A to the power N alpha, and A to the power N is 1 because N is the order of A. So this is 1, right? So that trivially implies the fact that order of A divides N by D, right? Okay. Now for simplicity, we assume, let Y be A to the power K. Okay, let Y be A to the power K. Then what is Y to the power beta? Beta is this value. What is Y to the power beta? So Y to the power beta can be written as A to the power K beta, right? So now K is basically D alpha, right? So this is A to the power K alpha beta. But obviously you can associate and commute to write it as A to the K is D alpha. So you can write it as D beta alpha, right? So that is basically 1 again. Okay? So that means order of Y, that is basically order of Y to the power K, order of A to the power K. So it divides beta, right? This is one more fact we have achieved, right? Clear? Okay. Now let order of Y be gamma. Okay. Then A to the power K gamma, that is Y to the power gamma, that is equals to Y to the power gamma. So it's 1, right? It's 1. But we know, since the order of A is n, therefore n must divide K gamma, right? N must divide K gamma. Now if I write n as D beta and K as D alpha, so this implies n can be written as D beta and K can be written as D alpha gamma, right? Obviously D will cancel out because D is clearly non-zero, being a GCD, right? So we have beta divides gamma, alpha gamma. Now previously we had beta and alpha assumed like they are co-prime numbers, right? So since beta and alpha are co-prime, they have no common factors. So beta will obviously not divide alpha in any way. So that implies beta divides gamma, right? But we have from here, so this is typically speaking that beta divides the order of A to the power K, right? Right. So if I name this to be 1, if I name this to be 2, therefore 1 and 2 implies that beta must be equal to order of A to the power K, and so that implies order of A to the power K. What is beta? Why the definition? So beta was so it was n was equals to D beta, right? So beta is nothing but n by D. That is what we actually required to prove. Right? And then the rest of the part is pretty obvious, right? Okay. Now some obvious observations which we can speak about from here is that suppose you have say let G be a cyclic group generated by X such that the order of X is infinite. Okay, then it's pretty obvious. You can notice that G is generated by some x to the power k if and only if. Now we have the fact that so obviously notice that if order of G is some n and G is this, then order of X is n as well. And the converse part is also true, right? Because that is, if you have an element with order n and you form the cyclic group, then the cyclic group also has order n, right? So obviously if G is generated by this element of order n, then G can be generated by an element x to the power k if and only if x to the power k has the same order as x, and that is only possible if GCD of k and order of x is 1. But in this case, since order of x is infinity, so the only possibility of this to happen is when k is equals to plus minus, right? Right. So this is one obvious observation, and the other obvious observation is obviously stated as the corollary. There is one more obvious observation we can speak about, which is that, so if G is, so suppose G has a finite order. Okay. Suppose G is generated by X such that order of X is equals to it. Then G is generated by x to the power k if and only if GCD of k and n is 1. So obviously then we can speak about the number of, therefore what are the number of generators of G? So the number of generators of G, so basically speaking, the generators of G are all those elements of the form x to the power k such that k and the order of x are co-prime, right? So this is equal to number of co-primes of n, right? Number of co-primes of n, and that is nothing but the Euler-Stoichhian function, right? So this we know, this is the Euler-Stoichhian function. Euler-Stoichhian function. This gives you the number of elements co-prime to n, right? So obviously, if you are given a finite group with a certain generator, then we can obviously find all the generators, all the number of possible generators, the number of possible generators of that cyclic group using the Euler-Stoichhian function. Right? So if I have an integer of this form, say it's p1 times alpha 1, sorry, p1 to the power alpha 1, p2 to the power alpha 2, and so on till some pk to the power alpha k, where p1, p2 till pk are distinct primes, then the Euler-Stoichhian function has the formula n times 1 minus 1 over p1 times 1 minus 1 over p2, and so on till 1 minus 1 over pk. Clear? So you can obviously use this. Yeah, got it. So why do we an applicative portion of this can be of this form. Suppose you have this group, say Z4. Okay. Now we know that Z4 can be generated by the element 1 because the order of 1 is 4 in Z4. Since Z4 is an additive group, so obviously the concept of order relies on the additive notation. So in case of an additive notation, you have NA equals to 0 sort of a concept. If n is the smallest positive integer such that this happens for some element a in the group, then n is obviously the order of the element. So obviously observe that 4 is the smallest element such that 4 times 1 equals to 0 in Z4. So 4 has the, so 1 has the order 4. Okay. Now we can also say that this the cyclic group is same as this cyclic. And the reason is pretty obvious to notice, because notice that what is 3? So 3 is basically 3 times 1, right? The order of 1 is 4. Observe that 3 and 4 are co-prime. So 3 and order of 1 are co-prime. So that means Z4 can also be generated by 3, and obviously it is also generated by 1. This is the fact. Right? Here you have 3 times 1, so this can be compared to the fact that you know x can be written as, or rather y can be written as x to the power k, where x is 1 and k is this multiple. Sort of a thing. I just wanted to say how we are comparing this fact. So this is the additive notation of writing. This is pretty obvious, right? Okay. So this is the fact. So that actually helps us to list the subgroups less as it should be. Because if we list the subgroups Z4 as 1 and 3 both, then it will trivially come to our mind that these two are the same things, right? So there is no possibility of writing identical subgroups twice, because in the lattice concept what we actually do is we try to draw a graphical structure of the group we have in terms of its subgroups. That is the only thing which we do. Okay, so let me come to the lattice concept. Okay, the lattice concept. So what is basically the lattice concept? So it's the graphical representation. So it's the graphical representation of the structure of the groups of the group which depicts a relation between the subgroups. Which depicts a relation between the subgroups. Clear? Okay. First, let us just give a quick example, and then we will be obviously having the algorithmic or the constructive concept. Okay. So let's give a example first. Suppose you have the group Z8. What are the elements in Z8? So you have, so you have 0, 1, 2, 3, 4, 5, 6, and 7. Right? Or rather, if I am writing Z8, I don't require the notation of a residue class. Let me just simply list the elements as they should be. So it's 0, 1, 2, 3, 4, 5, 6, and 7. Clear? Okay. Now obviously Z8 is generated by 1, and 1 has the same order as 3, 3 has the same order as 5, and 5 has the same order as 7. So just considering one of these 4 is enough, right? Now what we do is that we draw an edge. We draw an edge downwards, starting from a group to one of its subgroups. So 1 has the subgroup which is generated by 2. 2 has the obvious subgroup generated by 4, and 4 has the obvious subgroup generated by 8. So this is an example of a lattice diagram, and obviously the subgroup generated by 8 is nothing but the trivial subgroup 0. Right? Right? Because you can notice the following fact if you have enough knowledge about Z mod nz or Zn to be precise. If you have the G to be the group Zn, we can also take it to be taking into isomorphic to the group Z mod nz. Then typically how are these subgroups constructed? Okay, so these are the subgroups are basically the factors of n, which you can obviously observe from here. Okay, so Zn is generated by 1. Then we keep on listing the factors of n, starting with the most trivial factor, that is the smallest prime factor we start with, and we keep on going. In case of the even numbers, it's quite linear because the only factors you have are the multiples of 2. So if n is even, then obviously you will have the smallest prime factor. You have 2, generated by 2, then you have 2 square, then you have 2 cube, and so on it continues. right? I'm not going to prove this fact at this moment, but you can obviously think of it just by using the Lagrange's theorem. There is nothing too specific about it. Similarly, if you have zp to the power n, okay, then the subgroups, so it's generated by 1, and all the other subgroups are just divisors of p to the power n, starting with the smallest one, smallest prime, which is the subgroup generated by p. Then you have the subgroup generated by p squared, and so on. It continues till p to the power n minus 1 and till p to the power n, and that is nothing but the zero subgroup. Clear? So I think you are having a pretty simple understanding of how the lattice structure actually works, right? So suppose let us consider Z6, right? So what happens in Z6? So Z6 is generated by 1. Now what are the two distinct prime factors which divide 6? So they are 2 and 3. So obviously they will be disjoint subgroups, right? So one has two disjoint subgroups. So one is the subgroup generated by 2 and one is the subgroup generated by 3. And what is the next possible subgroup? The next possible subgroup is the subgroup 6, right? And so 6 is a direct possible subgroup of both these cyclic groups, 3 and 6. So we can write it like this, right? And this is nothing but the zeroth subgroup. Similarly, let's consider Z12. So Z12 is generated by 1. So it has two distinct subgroups which are 2 and generated by 2 and generated by 3. Then the other possible subgroup. So we are going through the factors of 12, right? So we have 1, 2, 3, 4, 6 and 12, right? So 4 will obviously be a subgroup of 2, right? 4 will obviously be a subgroup of 2, and 6 is also a subgroup of 2 because obviously 2 divides 6. So m is a subgroup of n if and only if n divides n. Right? You can also consider this as an exercise. Also pretty easy to notice if you have just clear idea of what is the structure of a cyclic, what are the elements in a cyclic, right? And obviously since 3 divides 6 as well, so 6 is also a subgroup of 3, but that is the only possible subgroup of 3, right? And both of them have a direct subgroup 12, which is again the trivial zero subgroup, right? So these things are clear. Okay. Now if I give you the construction of how this construction works, then it will be far more theoretically understandable. So let me just give the construction. The construction is fairly done in an upward direction. Okay. So what we do is that construction of lattice of a finite group. Okay. So what we do is we plot all the subgroups of G, starting at the bottom with the trivial subgroup, which is the subgroup generated by the identity, and ending at the top with the group G. So whatever we are doing is that we are starting with this subgroup, and we have the at the topmost position we have the group G, and every other subgroup relies within these two things. Yeah, and that is also pretty obvious. Okay. Okay. So plot all the subgroups of G starting at the bottom with the subgroup generated by the identity element, ending at the top with the graph with the group G, with the subgroups of higher order residing above the ones with lower order. That is, if a subgroup G1 is here and if a subgroup G2 is here, then G1 has more number of elements than G2, right? Clear? Draw paths upwards, that is like this, draw path upwards between subgroups, using the rule that there exists a line upwards from A to B if A is a subgroup of B, right? And there does not exist a subgroup containing A and contained in B, or I should say properly containing A and properly contained in B. So obviously you had this subgroup 2 and you had this subgroup 4. So we had joined 4 and 2 in an upward direction. Let me just draw it in an upward direction only. So we had drawn them like this, and we had this edge just because we know that 4 is a subgroup of 2 and there is no other subgroup which is present in between 4 and 2 such that that is properly contained between 4 and 2, right? Okay. Now further notice that if A is a subgroup of B, then there exists a path upwards from A to B containing a chain of intermediate subgroups, right? Containing a chain of intermediate subgroups, right? Containing a chain of subgroups. So for an example, you had so you had G equals to say Z12. Then you had, so let me just write it here like this. So you had E here, that is 0, right? Then you had 2 and 3, right? Okay. Now obviously notice that what is the order of 2? So order of 2 is basically 6 and the order of 3 is 4. Okay. So obviously you should write 2 below 4 technically, but since they are disjoint it won't matter actually. Okay, so let me just okay, so yeah, so we have 2 here, yeah, let's say 3 here, then we have 4, 6, and these are the only possible subgroups, right? So now Z12, so 2 is a subgroup of Z12, so we can draw this line. 3 is a subgroup of Z12, we can draw this line. 4 is a subgroup of 2, 6 is also a subgroup of 2, 3 is also a subgroup, 6 is also a subgroup of 3, and this is a subgroup of 4 and a subgroup of 6. Now obviously 0 is a subgroup of 2, so it has a path from 0, we have a path from 0 to 2, we have a path passing through 4, right? Similarly, it's a subgroup of 3, so we have a path from 0 to 3 passing through 6. That is the PD. And the reason behind is that if A is a subgroup of B and B is a subgroup of C, then obviously A is a subgroup of C as well, and that's pretty easy to notice, right? Observe that for any pair of subgroups H and K, this, what is the smallest subgroup containing both H and K? The smallest subgroup containing both H and K denoted as HK is the immediate mutual join of H and K. That is basically speaking. So suppose you have two subgroups H and K, and here you have a subgroup A, then you have a mutual join. So H is joined to A and K is also joined to A, and there are no intermediate subgroups in these paths. That is, there is no intermediate subgroup between the in the join of H and A and K and A. Then A is nothing but the smallest subgroup containing H and K. So in this case, obviously notice that the mutual join of 4 and 6, the smallest mutual join of 4 and 6 is nothing but 2. So 2 is the subgroup which is, so it's 4 comma 6, right? It's the smallest subgroup containing both 4 and 6, both these subgroups 4 and 6. Clear? Or we can consider them writing as follows. So we can think of it like trace paths upwards from H and K till we reach a mutual join. A mutual join, say A. If A is the immediate mutual join, if A is the immediate mutual join, then A is this, else if there exists some A1 subgroup of A such that A1 is the mutual join, then A1 is the required sum. So the basic thing which we want to depict here is of this form, let's say. So you have the two subgroups H and K. Suppose H is joined to A, K is joined to B, then A is joined to C, B is joined to D, and C and D both are joined to E. Then the mutual join of H and K, the smallest mutual join of H and K is E, because H is joined to E and K is joined to E via these paths, and E is the smallest such subgroup to which H and K both are joined. Below E there are none, so E is the subgroup H. That is what I mean. Right? So by a symmetric process we can obviously read off the largest subgroup which is contained in both H and K, right? By a symmetric process we can read off the largest subgroup contained in both H and K. Okay, so you have, so let us come up with this example. Yeah. So let me just write it once more. So you had Z12, so it's 1, then you have here 2, you have here 3, then you have here 4, 6, and this, and then you have the, right? So what is the largest subgroup contained in 2 and 3? Right? So the largest subgroup contained in 2 and 3 is, you just look downwards from 2 and 3 and find the immediate mutual join. So if you look downwards from 2 and 3, so the immediate mutual join you have of 2 and 3 is 6. So that's basically this, right? Got it? Yeah. So that's the lattice concept. Right? It's clear? So let me just end this lecture with a few examples. Okay. So examples. So let us start with key 4. So the Klein 4 group. It's also called the V4 group as well. I don't remember the pronunciation exactly. It was something of Virgrep, right? So K4 it can also be written as V4. So it's courtesy to some VIERGRAPPE. Yeah. So it consists of the element 1 A B C such that A squared is equals to 1, B square equals to 1, and C square is also equals to 1. And it obviously you can notice that C is nothing but AB. You think of C like that. Right? So what is the lattice diagram of it? So the only possible subgroups of K4 are the subgroup generated by A, subgroup generated, or let me come up with the constructive procedure. So you have K4 and you have the identity group 1, right? Now 1 is the immediate subgroup which contains 1 is A, B, and you have C as well, and they are immediately subgroups of K4. So this is the lattice diagram. I won't be following this procedure anymore because I think it's pretty visually understandable. Clear? So it's K4. Suppose we talk about S3. Then S3 you have you have it generated by 1 2, the cycle 1 2, the cycle 1 3, the cycle 2 3, and the cycle 1 2 and 3. So these are the possible subgroups, right? They are the possible subgroups, and then the other subgroup which is contained in all of them is the subgroup generated by 1, right? Okay. Then the other important one is the Q8. Q8 is a very important example because every subgroup of it is cyclic. In fact, we can say that every subgroup of it is abelian, but Q8 is itself not abelian. Okay, so it is the quaternion group. Q8, it is the quaternion group. Okay, so it consists of the elements 1 minus 1, I minus I, j minus j, and k minus k. Other compact way of writing it is plus minus 1, plus minus I, plus minus j, and plus minus k. The properties are such that, so we have ij equals to k, jk equals to I, and ki equals to j. And if I reverse the notation, that is, if you have ji, then that's minus k. If you have kj, then that's minus I, and you have ik, then it's minus j. Okay. Then also you have I squared equal to 1, j squared equal to 1, and k squared equal to 1. Okay. Okay. So I squared is minus 1. Sorry, not 1, it's minus 1. Yeah. I squared is minus 1. J squared is also minus 1, and k squared is also minus 1. We will be having this pretty easily here. You can think of them as being the relative to the complex numbers. Okay. We'll be getting this point like this. Pretty easy to understand, nothing of that difficult sort. So yeah, so the thing is of this sort that the cyclic group generated by I, so it's 1 minus 1, I minus I. So 1 is nothing but I to the power 4, minus 1 is I cubed, I is obviously I to the power 1, and minus I is I, sorry, yeah, minus 1 is I squared, sorry, minus 1 is I squared, yeah, and minus I is I cubed, right? On a similar basis, you can form the cyclic group J, which consists of the element 1 minus 1, j minus j, and you have k, which is 1 minus 1 and k minus k. And obviously you can notice that these are the only possible subgroups, immediate subgroups of Q8, right? So Q8 has the immediate subgroups as I, J, and K. And IJK has the immediate mutual subgroup as the subgroup, so it's the subgroup 1 minus 1, right? Or you can think of it as the subgroup generated by minus 1 directly. You can think of it as the subgroup generated by minus 1. Because minus 1 has order 2 and it's inside subgroup generated by 1. Clear? So notice that this and these are cyclic subgroups This also a cyclic group, this also a cyclic group. So all these subgroups are cyclic. In fact, abelian, but Q8 itself is not abelian, because you can obviously notice it from this fact that Ij is not equal to Ji. Right? So it's a pretty important group. The last group we will be studying is a bit complex to draw, because that doesn't give a planar graph. So planar graph is in a way you can think of it like you cannot draw the graph on a paper without the edges intersecting each other. Okay, a graph is called a planar graph if you can draw that on a plane, on a surface where the edges do not intersect. It is no more a planar graph if the edges intersect when they are being drawn on a plane. Because if you don't draw them on a plane, if you kind of structurize them in a 3D surface, then the edges obviously do not need to intersect, right? You can just bring one edge from the top and the other edge from the bottom, right? They do not intersect on a 3D plane, in a 3D region, but over a plane they will obviously intersect. So that no more remains a planar graph. So D16. So obviously we will use the notations of R being the rotations and S being the reflections. So D16 is basically D8. Okay. So the elements, if I just write them, so they are 1 R squared, R cubed, R to the power 4, R to the power 5, R6, R7, and then you have S, SR squared, SR cube, SR to the power 4, SR to the power 5, SR to the power 6, and SR to the power 6. Right, so let me just draw them. So D16, the immediate subgroups you have of D16 are the one generated by S and R squared, the one generated by R, and the one generated by SR and R, SR and R squared. Yeah, correct. Okay. Then SR and R square has the immediate subgroup SR square and R to the power 4. Then you have SR to the power 4. From R you have this immediate subgroup R square, which is also a subgroup of this, and it will also be a subgroup of this because R square is there, right? The immediate subgroups of this being SR cube, R to the power 4, and this being SR to the power 5, R to the power 4. Yeah. Then from here you can bring out the immediate subgroup SR to the power 6. Here you have SR squared. Then from here you have, I guess, SR to the power 4 and S, right? Right. From here you have R to the power 4. But obviously R to the power 4 is a subgroup of both of them, right? So here you notice them intersecting, right? Right. Similarly, it will be a subgroup of this as well. And they have the immediate subgroups SR cubed and SR to the power 7. From here you have SR to the power 5 and SR, yeah, correct. No commas in between, SR, right? But R to the power 4 is a direct subgroup of this as well, right? And each of these are linked to only one subgroup, so it is linked to, yeah. Yeah. So it's linked to subgroup. Okay. So obviously you can notice that there are intersections, right? There are intersections, and you obviously have no procedure to just overcome these intersections. They will be there until and unless you draw it in a 3D region. You remove it from a plane. Okay. So D16 is the lattice. The lattice of D16 or D8 is not clear. Is it clear? Is it clear? Okay. I'm not actually discussing about the concept of conjugacies in SN in this lecture. We will be coming up with a new lecture on completely dedicated to conjugacy because that's not a difficult topic. That's a very short topic to discuss. Okay. Yeah. So meet you guys in the next lecture.